discussed from chapter 15, for those of you who took physics 185 from me, is because in chapter 32, you see that again. And if you understand it from physics 185, then chapter 32 is like a piece of cake. Then it's not intimidating. So, an expression like this, any function, so any function of x plus or minus vt describes a disturbance that travels, a disturbance that propagates. So any, I don't care the form of it. Over here, this is a sinusoidal function, right? You have a sine or a cosine, they're called sinusoidal harmonic functions. But any function of x plus or minus some number multiplied by time, right, represents a disturbance or wave that travels. So when you see this x plus or minus vt, right? So the x tells you the axis along which the wave travels. It's the axis along which the wave travels. In other words, it travels along the x-axis. The v that you see here is the speed at which the wave travels. How fast is the speed at which the wave travels. Time is time. Now, I should write it like this: plus or minus x plus or minus vt. These signs over here together, this sign, the sign of x and the sign of vt together, determine. So the x means that the wave travels in the x-axis. The question is, does it travel in the positive x-axis or in the negative x-axis? And it's these signs, the sign of x and the sign of vt, that combination will determine the direction along the x-axis that the wave travels. They determine the direction along the x-axis, in this case x-axis because of that x, that the wave travels. So if you have plus plus or minus minus, like x plus vt or minus x minus vt, if the two signs are equal, plus plus or minus minus, how about I say equal signs? Means if the signs are equal, the wave travels in the negative x direction. But if the signs are different, then the wave travels in the positive x direction. So plus plus minus minus, it's going in the negative x-axis. But plus minus or minus plus, it's traveling in the positive x-axis. So, I don't know, so those of you who took a course from me for 185, I have a statement in there to that effect. Here it is. I wrote, if x and vt, this is from chapter 15, if x and vt have the same sign, plus plus minus minus, then the wave travels in the direction that x decreases, that's the negative x direction. But if x and vt have opposite signs, then the wave travels in the direction that x increases, that's the positive x direction. And when you write down an expression like this, where is it? Then this here is the maximum value of this, right? Because what will be the maximum value of this function? It's going to be a times the maximum value of the sine. But what is the maximum value of the sine of any angle? But what's the maximum value that the sum function could ever have? 1. So 1, which is the maximum value of this, times a will be the maximum value of this. So this is called the amplitude, which is the maximum value of this. So this is the amplitude of this quantity, the highest value of whatever is on the left side. So the sine of kx and the sine of omega t will tell you in which direction of the x-axis the wave is traveling. K, the number, the parameter that multiplies the position, x, y, or z, or r, this k is related to the wavelength of the wave by this expression, 2 pi over lambda. Lambda is the wavelength of the wave. K is called the wave number. And then omega, the coefficient of time, is the angular frequency, which is related to the frequency, which is the number of oscillations per second, which is related to the period, which is the time for one oscillation. So omega, the angular frequency, is related to the frequency and is related to the period of the wave by that equation, and the coefficient of the position variable here, x, y, or z, or r, like, that coefficient is related to the wavelength of the wave, right? And if you multiply the wavelength of the wave by the frequency of the wave, you'll get the speed, which is this guy over here, right? How fast the wave travels. So the speed here is lambda times f, which is lambda over t, which is also written as omega over k. That's the speed for which the wave propagates. So written in this form, the coefficient of time, with no coefficient over here for x, this is the speed at which the wave travels. Written in this form, with a coefficient, for x, then the speed at which the wave travels is this coefficient omega divided by that other coefficient, k. Those of you who took 185 from someone else, did you get to learn this about waves? So the idea is, can you look at a mathematical expression and then right away be able to answer many questions related to that wave description by that mathematical expression? So the reason why it is important is because in chapter 32, we talk about the propagation of electromagnetic waves. So let me go to page 280. And when you look at chapter 32, this is like a review of many of the things that we talked about in this course. It begins with, they're called Maxwell's equations. And so the first of Maxwell's equations is actually Gauss's law. So, we spent chapter 22 on Gauss's law. So, basically here, the message is that electric charges give rise to electric fields. And we talked about specific cases. If the charge is positive, we say the electric field is a vector that points away from the charge. If the charge is negative, the electric field that it produces is a vector that points towards the charge, If you write Gauss's law, but you replace the electric field with the magnetic field, then on the right-hand side of the equation you get 0, which simply means that there are no magnetic charges, magnetic monopoles in nature. So something else must produce magnetic fields, not magnetic charges. And then, so what we did to calculate magnetic fields in chapter 28 is we wrote the Biot-Savart law, which relates the generation of a magnetic field due to a constant current, right. So a current gives rise to a magnetic field, but what is a current? It's electric charges in motion. So magnetic fields at the fundamental level are produced by electric charges in motion. Right? And we talked about Faraday's law in chapter 29. And then Ampere came along. This was discussed, I think, in chapter 29:2, I think. And he added something to, Maxwell came along and he added this term to Ampere's law. So basically he said that magnetic fields can be generated by moving electric charges, but magnetic fields are also associated with a time-changing electric field. So there's a whole chapter dedicated to that, and problems and so on. So Maxwell came along and he manipulated these equations, and he was able to show that the electric and magnetic fields, when you consider the four equations with his correction to Ampere's law, the electric and magnetic fields satisfy equations like this, which he recognized as a wave equation, a disturbance that propagates in space as time goes on. And these coefficients, mu naught, epsilon naught, are related to the speed with which the wave propagates. So he just equated 1 over the speed square is equal to mu naught epsilon naught, and then was able to solve for the speed of the electromagnetic waves propagating in vacuum. And to his surprise, he obtained the value for the speed of light, which is an indication that light can be thought of as an electromagnetic wave. So, so light travels in vacuum at 3 times 10 to the 8 meters per second, right? It depends on the values of the electric permittivity of free space, epsilon naught, which we saw in Gauss's law, and the magnetic permeability of free space, mu naught, which we saw in Ampere's law and also in the Biot-Savart law. So, these parameters associated with vacuum determine how fast electromagnetic waves propagate through vacuum. But a lot of this is just like a little brief summary of some things that we talked about in class from various chapters. And all I say is that if you mathematically manipulate these equations, you do something, you play with it. I just said you play with them. It's a lot easier. It's actually done in the textbook in chapter 32, but don't waste your time with that. There's a more refined, shorter way of deriving Maxwell's equations using the del operator, and once you learn how to do it that way, you don't even want to look at how it was done by the authors of the textbook. I mean, the authors of the textbook did it using the integral forms of Maxwell's equations because they assumed that the students reading the book at that level would not be familiar with the del operator, with gradients and divergences and curls. And so that's why they did it that other painful way, but with the, if you know about divergences and gradients and curls, then in half a page you can derive Maxwell's equations very, very, very quickly using the differential forms of Maxwell's equations. So all I said here is just by mathematically manipulating them, whatever that is, right? Then you obtain these wave equations. And since we learned in chapter 15, or those of you who what the solution to this wave equation is, you can just write down what a solution of an electromagnetic wave equation would be. So for example, in this picture, right? If I write something down like this is the electric field at position X at the instant of time t. So whatever multiplies, in this case I wrote it as a cosine function. I could have also just written it as a sine function. What is the maximum value of the cosine function? So what would be the maximum value of the electric field? Well, the electric field is going to have its maximum value when the cosine function gives you 1. And 1 times this parameter, this is therefore the amplitude of this quantity. So E max is just, not E naught, like initial. It's E max. It's the maximum value of the electric field. Because, right, the ultimate maximum value of the cosine of whatever is in here is going to be 1. And 1 times that is going to be the maximum value of this. So it's called the maximum value of that. It's called the electric field amplitude. And for magnetic fields, you write the same expression. Except that you have a magnetic field amplitude. But you look at this expression, and there's so much that you can figure out from here. So first of all, whatever multiplies x, that's the wave number that's related to the wavelength of the electromagnetic wave. Whatever multiplies the time variable here, this omega, is the angular frequency, which is in radians per second, which is related to the frequency in hertz. And whatever the frequency in hertz is the period in seconds, right? This is the amplitude of the magnetic field, amplitude of the electric field. And from looking at these expressions, can you tell me in which direction this wave is propagating? If I use this expression for the electric field of an electromagnetic wave, and this expression for the magnetic field of an electromagnetic wave, in which direction is this electromagnetic wave propagating? So you look over here, if the signs are the same, it travels in the negative x direction. If the signs are opposite, different, it'll travel in the positive direction of this. Well, this is plus and that's minus, so they're different. So the wave travels in the positive x direction. And that is what we have over there in the picture. You have an x-axis to the right, a y-axis up the page, and a z-axis out of the page. And you see for the x-axis over here, direction of motion of the wave. So that's the direction in which the wave is traveling. But notice something interesting. The electric field points along the y-axis. When the cosine function is positive, the electric field is going to be pointing up. When the cosine function, which is half of a cycle, right, the other half of the cycle, is negative, the electric field is going to be pointing down. So as the wave propagates to the right, the electric field is like up, 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 flips, 0, flips, down, 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 biggest, that's the amplitude, smaller, 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 0, flips, up, 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 amplitude. Up, 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 but smaller, 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 0, flips, negative, 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 biggest, negative, amplitude, negative, 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 small, 0, flips. So the electric field is oscillating like this. Right? So see, when it gets to the top, it doesn't flip. No, as you know, it comes down, pointing up, 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 up. When it reaches 0, it flips, and then it goes down, 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 down. When it gets to the bottom, and then it continues pointing downwards. It gets to 0, but still pointing downwards. The flips only at 0. So that is what the red arrows indicate. This would have been a good day for my laser pointer, but that's when the red arrows indicate. But I left it in the office. Okay. So you see, it goes up, up, up. That's the biggest. This is the electric field amplitude here, but then still up, up, 0, flips, and then down, down, down. Biggest. This is the amplitude on the other side, right? But still down, getting smaller, 0, flips, up, up, up. So if you look at the red arrows, that represents the electric field of the wave. Now, notice that the magnetic field associated with this wave is perpendicular to the electric field. So the electric field, the magnetic field, points along the z-axis. So over here, you'll see that I wrote, instead of, you call the unit vector z hat. So the magnetic field is pointing out, and then it comes in, out, 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 0, flips, and then it goes this way to a maximum amplitude. And then still pointing that way, gets smaller, 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 0, flips, amplitude, smaller, 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 0, flips. And the electric field and the magnetic field are oscillating in phase. When the electric field has the maximum up, the magnetic field has the maximum this way. And they come together, and together they reach 0, and then they flip. And when this magnetic field reaches the maximum, this one reaches the maximum this way. Then together they come in, 0, and then they flip. So as the wave travels, so what happens is that the magnetic field is oscillating, right? And Faraday said that as the magnetic field changes with time, it gives rise to an electric field. But the electric field is changing, and Maxwell said as the electric field changes with time, it gives rise to a magnetic field. So electromagnetic waves can propagate from the sun to the earth, right, through the vacuum of space in between by this oscillating electric and magnetic fields. As one oscillates, it gives rise to the other one gives rise to the first, and they regenerate one another. But you look at an expression like this, and there's a lot that can be answered, right? If I write an expression like this, for example, if I tell you here is an electric field, and this is 10 volts per meter, cosine of 2x plus 8t. So what can you tell me? What's the electric field amplitude?
10 meters.
10 volts per meter. Yes? What is the wave number?
2.
And this should really be radians per meter. And this tells me what the amplitude is what the wavelength is gonna be. The wavelength is 2 pi over k. So that would be 2 pi over 2. So this is going to be pi meters. So this would be 3.14 meters. That would be the wavelength. What about omega? What's the angular frequency of this wave? Actually, I just put this randomly, right? I mean, this divided by that is going to be the speed. It should come out to 3 times 10 to the 8 meters per second, but let's just say this is traveling in some medium, not vacuum, right? So what's omega? It's 8 radians per second, right? So from this you can get the period. The period is 2 pi over omega. So it'll be 2 pi over 8. So it'll be pi over 4. So 3.14 over 4 seconds per cycle. And the frequency will be 1 over that, 1 over the period. So it'll be 4 divided by 3.14 hertz. In other words, what I'm saying is that I can write down an expression like this and answer many questions associated with it. And I can ask, what is the speed of propagation of this wave? Well, you can either do lambda times f, or you can do lambda divided by the period, or you can do omega over k. Omega over k is simplest because you can just read off omega as being 8 and k as being 2. So this would be 4 meters per second. So how about for the extra credit, I throw in a problem with some mathematical expression, and then I can ask you various questions like this, and then just tell me what the values are. Oh, another thing is this. When you write, you see this expression here? What this means is that you can, if you know the magnetic field amplitude, I can tell you what the corresponding electric field amplitude is going to be. All I need to do is multiply by the speed of the wave. If I multiply the magnetic field amplitude by the wave, I can then tell you what the electric field amplitude is going to be. So there's a connection like that. I mean, I'm not showing that, but that's what that is.
Doesn't C typically represent a speed of light, though? Like
in vacuum.
Okay.
But if light is traveling in water, it's not called C. Light travels more slowly in water than it does in vacuum. So it's not called C, it's called V. The speed of light in glass is even slower than the speed of light in water and in vacuum, so it's called V. So
Okay.
V is the speed of the wave, It's just that for the specific medium of vacuum, it's called C.
So that C is not.
This C will be for the relationship between the magnetic field amplitude and the electric field amplitude as the wave travels in vacuum.
Okay.
Like in this picture over here, if I ask you, what is the magnetic field amplitude? Then you would say, oh, well, Emax. In this case, well, if the speed travels at 4 meters per second, it's not traveling in vacuum, right? So then you would say V max. Right? This is 10 volts per meter, and this is V, which is 4 in this problem, right? Because 8 divided by 2 is 4. And this is V max. So the magnetic field amplitude would be 2.5 Tesla. Yeah? So that's what this is saying. So again, if you learned in Physics 185 how to, you're given a mathematical expression that represents a mechanical wave, right? Then there are many questions that you can answer by just looking at the expression. You can figure out, many, you can answer many questions. And that discussion carries over to the description of electromagnetic wave propagation. It's just a different type of wave, right? But you still have an amplitude, you still have a frequency, you still have an angular frequency, you still have a period, you still have a wavelength, you still have the speed with which it travels, the direction in which it travels. All of those, it's just the same. And then there is this topic on what is the intensity that the wave transports. So one defines this quantity called the pointing vector. And pointing is not like I'm going to point with my fingers. This is somebody's last name actually. Notice it's got a Y, not an I. So it's not like I'm pointing at you. There's a Y. So pointing is somebody's last name. And so the pointing vector S is obtained by calculating the cross product of the electric field and the magnetic field. Going back to this picture, since you are good with cross products, right? And you'll never forget it again. Look at this picture. In which direction? So take one specific instant of time. Suppose you take this instant of time. In which direction is the electric field pointing? Electric field.
Okay.
Up. Y-axis, up. What about the magnetic field?
Z-axis.
Out. So what is this? Cross this.
Right.
This way. Let's look at another instant of time. How about I look over here? At this point over here, the electric field, that's the one in blue, the electric field is into the page, right? Sorry, the magnetic field is into the page. That's the one in blue, and the electric field is down. What is E cross B? E cross B.
Right.
Right? So notice, it's like as the electric field is doing this, it's like the magnetic field has to keep track of it so that E cross B comes out in the direction that the wave travels. So if you know the direction of the electric field vector and you know the direction of the magnetic field vector, then you should know, well, then in which direction the wave is traveling, the wave is propagating. And you probably learned about transverse waves and longitudinal waves in Physics 185. A longitudinal wave is when whatever is vibrating associated with the traveling wave, if the wave if the vibration occurs along, like right, left, along the direction of the wave travels, it's called a longitudinal wave. But if the vibrations occur perpendicularly to the direction in which the wave travels, it's called a transverse wave. So this shows clearly that both the electric and the magnetic fields in vacuum vibrate perpendicularly to the direction that the wave travels. So electromagnetic waves are examples of transverse waves. So Poynting wrote this expression. Yes.
If that was a sine instead of cosine, would we get the same value?
Yes. Mhm. Because if this is a sine, then the magnetic field would be written as the magnetic field amplitude, which would be 2.5 sine. And then the argument is the same, 2x plus 18. So for this expression, for the, and this, let's say this electric field is in the y direction, so like this. Well, plus y minus y plus y minus y. The magnetic field would be, in this case, 2.5 Tesla, and then everything else is the same. Except that the wave is traveling according to this sign, and this sign, plus plus, in which direction is the wave traveling?
Negative direction.
In the next, so if the wave is going this way, what would have to be the direction of the magnetic field when the electric field is up? E cross what is going to keep me a wave traveling that way?
Into the board.
Into the board, and into the board would be minus z hat. So that will be the expression for the magnetic field. Yes? No? Because E cross B points in the direction that the wave travels. So if I write an expression like this, plus 2x plus 8t, the plus of the plus, tell me, equal signs is in the negative x direction. Of x, only because I wrote an x over here. So the wave travels this way. But if I write down an expression for the electric field like this, so this is plus, blah, 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 then I have a y, so when the cosine function is positive, the electric field is going to point up. But if the electric field points up and the wave goes this way, well, E cross what direction that's perpendicular to this will give me that. And it would have to be E cross this, E cross B, so B has to be this way. So that would be in the minus z direction. So Poynting, Mr. Poynting, wrote this expression for a vector s that points in the direction that the wave travels. Now the units of this is the units of s. So we have s, it's E cross B over mu naught. So this is in units of joules per second per meter squared. Well, what is joules per second?
Watts.
Watts, that's a power per meter squared. So this is, so, and these are the units, I don't know if you're familiar with that, but those are the units of intensity. So, but one has to be careful. There's the following. So this quantity S, which is called the Poynting vector, has units of intensity. But intensity is energy, which is a scalar quantity, over time, over area. So there are scalar quantities. So intensity is a scalar quantity. But this is a vector quantity. So the definition of intensity is you take the average value of this vector, and that's going to be some vector with some average value, and then you just take the magnitude of that average value of that vector. So the intensity is the average value of a vector. Which vector? The Poynting vector. So, you know, a vector has magnitude and direction. So the average value of that magnitude is the intensity, which is the energy transported by the wave in 1 second through a cross-sectional area of 1 meter squared. Is the intensity is joules per second per meter squared. Is the energy transported by the wave in 1 second, in a time interval of 1 second, through an area of 1 meter squared, where that area is perpendicular to the direction that the wave travels. That's the definition of intensity. And, you know, people memorize intensity equals power of an area or energy per unit time per unit area. And they memorize this, and it's a simple thing to remember. Or a formula like that is given in the book or in the test. But they don't really know what this means. They just want to plug in numbers. So think about it so that then you can answer questions associated with it.